We are in section 11.8, power series. Power series are a lot of different functions can be written as or approximated by a power series. These are easier to work with than other series. And so what a power series is going to be the sum from n equals 0 to infinity of c sub n x to the nth power, and the first term then would be just c naught plus c1x plus c2x squared plus c3x cubed, and so on, where x is our variable and c's are just constants. These are called our coefficients. The above equation is that of a power series centered at 0, and the sum of the series is f of x equals c naught plus c1x plus c2x squared plus c3x cubed plus and so on. The power series will converge for some values of x and diverge for other values. The domain of a power series function is the set of all x values for which the series converges. And so, a couple things to note: this is centered at 0, and also we'll talk about what that means a little bit more. And then also a power series converges for some values of x and diverges for other values of x. And so we'll be looking into that a little bit more. So a power series centered at A is going to be the sum from n equals 0 to infinity of c sub n times x minus a to the nth power. And so you can see that it is centered here at A. And so we have c naught plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed, and so on. Note that the series always converges when x is equal to a. So what power series look like? There's a couple examples down below. So expanding these both out, you would see that it would have that form like a power series would. So at the top of the next page, it says, remember from college algebra, geometric series are of the form the sum from n equals 0 to infinity of a times r to the nth equals a plus a times r plus a times r squared plus a times r cubed, and so on. And this is equal to a over 1 minus r. And again, it only converges if the absolute value of r is less than 1. So definitely a formula that we should know. And this says r is called the common ratio and is a constant value. And r needs to be between -1 and 1 in order for the series to be convergent. Extending this idea to a power series, we have f of x equals the sum from n equals 0 to infinity of x of n. And we would have 1 plus x squared plus x cubed plus, and this would go on forever. And this has a common ratio of x, and a is equal to 1. And so in order to do this using our formula up above that is circled, we would have f of x is equal to 1 over 1 minus r, or x, but only if x is in between -1 and 1, which is what's stated up above. And so the wording that's going to show up with power series is going to be along the lines of, this is our interval of convergence, meaning that we only converge between -1 and 1. And also, the radius of convergence would be equal to 1. And we'll talk about that since you're going out from this interval. If you were to think of that as that distance, that diameter, the radius of it would be half of it. So it would just be 1. And then we have a theorem right below. And the theorem says, for a given power series, the sum n equals 0 to infinity of c sub n times x minus a to the nth power, there are only 3 possibilities. And so these are the 3 possibilities that we have. The first one is that the series converges only when x is equal to a. The second one's going to be the series converges for all x, so that would be from -infinity to +infinity. And the third case, which occurs very often, which says there is a positive number r, which is called our radius of convergence. such that the series converges if the absolute value of x minus a is less than r. So it will converge in that radius and diverges if the absolute value of x minus a is greater than r. And so for this, if you think about this convergence part that we have here, this means that negative r is in between x minus a and r. And solving this for x, adding a to both sides, we'd have a minus r is less than x is less than a plus r. And so that would be that interval that would allow our series to converge. So the interval of convergence right below this says of a power series, the sum n equals 0 to infinity of c sub n times x minus a to the nth power is an interval that consists of all values of x for which the series converges. And so thinking about this, we would have this centered at a, and again, since it's centered at a, we would go with that radius of convergence, subtracting r and adding r. And so this right here is where it converges. And it converges for the absolute value of x minus a being less than r. And this is called our interval of convergence. So it's going to diverge otherwise. So it would diverge for anything smaller than a minus r or larger than a plus r. And so this diverges for the absolute value of x minus a being greater than r. So we do have a couple issues here where we need to check. So we do need to test endpoints and see, since it could be included, could not be included, endpoints to see if it converges or diverges for the series. And usually when we're working these out, we mostly are going to be using, just because of the way that they are set up, and especially since you notice with powers, is that we mostly use the ratio or root test. But again, not always, but this would be most likely. The example at the top of the next page says find the radius of convergence and the interval of convergence for the series. And so you'll note that the series is the sum from n equals 1 to infinity of x to the n over the square root of n. What's different from this series from all the other ones that we've dealt with before up through 11.7 is going to be that this one doesn't just have an n in it, which is that counter that we have going from 1 to infinity, but it also has a variable x. And x is what we're trying to figure out what values it needs to be between in order for this series to converge. And so in order to figure that out, I need to first figure out where it could converge, and looking at the different tests that we have that we've learned all the way up through 11.7. And so for this one, I'm going to use the ratio test, since we have a numerator that's raised to an nth power, but the denominator is not raised to an nth power. And so for the ratio test, we have a sub n, which is equal to x to the nth all over the square root of n. And then we also had to look at a sub n plus 1, which is equal to x to the n plus 1 all over the square root of n plus 1. And so looking at the limit as n approaches infinity, and it was a sub n plus 1 over a sub n, it's equal to the limit as n approaches infinity of a sub n plus 1, which is x to the n plus 1 over the square root of n plus 1. And instead of dividing by, I'm going to multiply by that reciprocal of a sub n, which is the square root of n, over x to the nth power. And so with this, we have the limit as n approaches infinity of, and you'll notice that in the numerator you have n plus 1 x's, and in the denominator you have n x's. And so n of them would cancel out, and you would just be left over with a single x. So we have x in the numerator times, and then our n variables, our n terms, are going to be the square root of n over the square root of n plus 1. And I'm going to rewrite this as a giant square root of the whole entire expression, which is n over n plus 1. And so the x that we have can actually move outside of the limit, since the limit is dealing with as n approaches infinity. But again, make sure that that x is in the absolute values. So times the limit as n approaches infinity of, and we have the square root of n over n plus 1. And this is also in absolute values. And as n approaches infinity, you can again deal with multiplying by 1 over the degree in the denominator, which would be 1 over n. And so this is going to equal the absolute value of x times the limit as n approaches infinity of the absolute value of the square root of 1 over 1 plus 1 over n, where again 1 over n would converge to 0. So we get the absolute value of x times 1, since this is what this limit is going to converge to. And this series is only going to converge if the absolute value of x is less than 1. And that means that our x value has to be between -1 and +1. So the next thing we need to do is test these endpoints to see if it's going to converge or not converge and diverge instead. So we're going to test, first one is going to be test when x is equal to -1, and then we are also going to test when x is equal to +1. And so testing when x is -1, I'm going to go ahead and substitute in -1 into my original series. So we have the sum from n equals 1 to infinity of -1 to the nth power over the square root of n. And for this, I noticed that it is alternating, so I'm going to go ahead and consider b sub n, which would be the positive part of this, which is 1 over the square root of n, which is going to be greater than 0 for all n greater than or equal to 1. So all of our terms are positive. We can also state that b sub n is decreasing, since the numerator is only 1 in those terms. As n gets larger, are getting bigger in the denominator, therefore smaller terms. So it's decreasing. The second thing that we have to have is that the limit equals 0 as n approaches infinity of 1 over the square root of n, which it does. So therefore we can say that the sum from n equals 1 to infinity of -1 to the nth power all over the square root of n converges by the alternating series test. So again, make sure to state which test we are using. So right now we know that -1, this value, we can include in that interval that we have. So right now we can say that x is going to be, for sure, it's going to be greater than or equal to -1. So now we need to test when x is equal to 1. And so we have the sum from n equals 1 to infinity of 1 to the nth power all over the square root of n, which just equals the sum from n equals 1 to infinity of 1 over, I'm going to rewrite this as n to the 1/2 power, which is a p series. And so since p is equal to 1/2, which is less than or equal to 1, this means that this series is going to diverge. And this is by the p series test. So that means that -1 we cannot include in our interval for convergence. So therefore it is greater than or equal to -1 since it converged at -1, but less than 1 since we cannot include 1, that other endpoint. And so our interval of convergence is going to go from -1 and including that to 1 and not including 1. Again, remember brackets we use to include and parentheses we use to not include. And then it also asks for our radius of convergence, which is r is equal to 1. So we have another example right below this. And that says, find the radius of convergence and the interval of convergence for the series. So again, radius of convergence, interval of convergence, and our series this time is the sum from n equals 1 to infinity of x minus 2 to the nth power all over n squared times 3 to the nth power. And again, not everything is raised to that nth power. So I'm going to go ahead and use the ratio test and try that again. And so we have a sub n is equal to, and this is x minus 2 to the nth power all over n squared times 3 to the nth, and then a sub n plus 1 is going to be equal to x minus 2 to the n plus 1 power all over n plus 1 squared times 3 to the n plus 1. And so the ratio test is going to be the limit as n approaches infinity of a sub n plus 1 over a sub n. And so we have the limit as n approaches infinity of a sub n, which is x minus 2 to the n plus 1 power all over n plus 1 squared times 3 to the n plus 1 times, and I'm going to multiply by the reciprocal of a sub n rather than dividing by it, which is going to be n squared times 3 to the n all over, and we have x minus 2 raised to the nth power. And again, this is all in the absolute values. So first thing I note is that the denominator has an extra 3. And since the numerator has 3 to the nth power, there's n of those, and there's n plus 1 in the denominator, we would have a 3 left over in the denominator. Likewise, we have x minus 2 terms, and we have n of them in the denominator and an extra 1 in the numerator, so x minus 2 would stay in the numerator. And then we have left over our n terms, so we have n squared over n plus 1 squared. So again, like the last one, the x minus 2 and the 3 are not dealing with that limit, so I'm able to pull those out in front of the limit in absolute values. So let's say absolute value of x minus 2 over 3 times the limit as n approaches infinity of the absolute value of n squared over n plus 1 squared. And now looking at our limit here, again, if you were to multiply both the top and the bottom by 1 over n squared, which is that degree that we would have in the denominator, you would end up with this converging to 1. And so from here, we are going to have x minus 2 all over 3. In order to converge, this must be less than 1. And the absolute value of the denominator is just going to be 3 itself. So another way to write this would be x minus 2, absolute value of that. And since the absolute value is only needed on that x, since that's our variable, all over 3 would be less than 1. So solving this and multiplying both sides by 3, we have x minus 2, absolute value of that, is less than 3. And so you can rewrite this and say that x minus 2 is going to be in between -3 and +3, which you can then, from here, add 2 to both sides of that inequality. and we end up with -1 is less than x is less than 5. So the next thing that we need to do is check these endpoints, and we need to test when x is equal to -1, and then also test when x is equal to 5 to see if it is going to converge at those endpoints or diverge. And so when x is -1, substituting that in, we have the sum from n equals 1 to infinity, and that's going to be -1 minus 2, which is -3, raised to the nth power all over n squared times 3 to the nth power. And so putting those 3's together, you can rewrite this as the sum from n equals 1 to infinity of -3 to the nth over 3 to the nth is the same as -3 over 3 all raised to the nth power, or -1 raised to the nth over n squared. And so this is alternating. It's an alternating series. So I'm going to consider b sub n, which is going to be 1 over n squared, which is greater than 0 for all n greater than or equal to 1. So all of my terms are positive. The second thing that we need to look at is going to be that b sub n is decreasing, and it is, since the numerator is consistently 1 and the denominator gets larger as n gets larger. The second thing that we need to check is that the limit as n approaches infinity of b sub n is equal to 0, which it is, since if the denominator gets really, really large, that would be 1 over something really large, which is practically 0. And so therefore, this converges by the alternating series test. So from here, we know that we need to include -1 since this value converged. So the next one we're checking is going to be when x is equal to 5. And so when x is equal to 5, we have the sum from n equals 1 to infinity of 5 minus 2 to the nth, which is going to be 3 to the nth, all over n squared times 3 to the nth power, which this is just going to simplify to the sum from n equals 1 to infinity of 1 over n squared. And since p is equal to 2 in this problem, which is greater than 1, we know that this will converge by p-series test. And so since this also converges when x is equal to 5, that means that we will also include that endpoint of 5. So our interval of convergence is going to go from -1 to 5. And then the radius of convergence is going to be r is equal to 3. So a few ways to figure out that interval is to check, to go through and use like the ratio, the root test are the most common we have, and then testing those endpoints. The radius of convergence, a couple ways to think about this. One is going to be that radius would be given by the value that the absolute value is less than that number. Or you can think about it as finding, since the distance goes from -1 to 5, that distance is 6. And so half of that distance would be a radius of 3. So we have some more examples on the next page. So the next one says to find the radius of convergence and the interval of convergence for this series. And this one is the sum from n equals 1 to infinity of x to the 2n over n factorial. So again, I would try to use that ratio test since not everything is raised to an nth power. And so for the ratio test, I have a sub n, which is going to be x to the 2n over n factorial, and then a sub n plus 1 is equal to x to the 2 times n plus 1 in parentheses over, and we have n plus 1 factorial. That 2 I'm going to go ahead and distribute through when I write my limit. So the limit as n approaches infinity of, and it's a sub n plus 1 over a sub n, which is equal to the limit as n approaches infinity of a sub n plus 1 is going to be x to the 2n plus 2 all over n plus 1 factorial times the reciprocal of a sub n rather than dividing by it. So I'm going to have n factorial over x to the 2n. So simplifying this, if you look at your x terms, you have x to the 2n, and then you have 2 extra x's in the numerator. So you would have x to the 2n plus 2. So the x squared left over, which again you can bring out into the front in absolute values. And then looking at the n terms, if you remember, n factorial means n times n minus 1 times n minus 2 times, and then so on down to 3, 2, 1. And n plus 1 factorial means n plus 1 times n minus 1 times n minus 2, and then all the way down to 3, 2, 1. And so you'll note that every single term here would cancel with every single term in the n plus 1 factorial, except for that n plus 1 term, and that would be in the denominator. So we have times the limit as n approaches infinity of 1 over n plus 1. And so now looking at 1 over n plus 1, as n goes off to infinity, this is going to converge to 0. So 1 over something really large would converge to 0. And so we would have the absolute value of x squared this time, not times 1, but times 0. And so this would equal 0. And so this is less than 1 for all x. And so this means that since it's always going to be less than 1, this means that we are going to be convergent for all x by the ratio test. And so this means that our interval of convergence is going to go from negative infinity to positive infinity, and our radius of convergence is going to be r is equal to infinity. And so this is a case where that limit is approaching 0, therefore it doesn't really matter what that radius or that value of x is going to be, and therefore it's going to be convergent no matter what value of x we have. So we have another example right below this, and this one says find the radius of convergence and the interval of convergence for this series. This is going from n equals 0 to infinity of n cubed times x minus 5 to the nth. And so for this one, I noticed too that not everything's raised to the nth power, so I'm going to use that ratio test again. And with the ratio test, we have a sub n, which is going to be equal to n cubed times x minus 5 to the nth power, and a sub n plus 1 is going to be n plus 1 raised to the third times x minus 5 raised to the n plus 1 power. So then looking at our limit as n approaches infinity of a sub n plus 1 over a sub n, we are going to have the limit as n approaches infinity of, and a sub n plus 1 is going to be n plus 1 raised to the third times x minus 5 raised to the n plus 1 all over n to the third times x minus 5 raised to the nth power. And so from here we need to simplify this, and you'll notice that there is n x minus 5's in the denominator and n plus 1 in the numerator, so 1 it will be left over in the numerator. And so this would simplify to just being x minus 5, which I can pull out in front of my limit since that does not have an n in it. Make sure to keep it in absolute values, times the limit as n approaches infinity of And in the numerator, we have n plus 1 to the third over n to the third in absolute values. And so again, you can multiply both the numerator and the denominator times 1 over that degree in the denominator. But you'll notice that both of those exponents are the same. So this is going to be converging to 1. And again, working it out more to see it if you need to. And so this is going to be the absolute value of x minus 5 times 1 is just that. And this is going to be less than 1 in order to converge, which means that x minus 5 is going to be bounded by negative 1 to 1, and then adding 5 to both sides, we get 4 is less than x is less than 6. And so from here we need to test our endpoints. So we need to test when x is equal to 4, and test the other endpoint, which is test when x is equal to 6. So when x is equal to 4, substituting that in, we're going to have the sum from n equals 0 to infinity of n to the third times, and it's 4 minus 5, which is negative 1 to the nth power. So this is definitely an alternating series. So we would let b sub n equal n cubed. And we notice that the limit of this, and your terms are not decreasing, and anything along those lines. So that using that alternating series test, I am stuck with. So I'm going to think about the test for divergence. And since the limit as n approaches infinity of n cubed equals infinity, we can say that this diverges by the test for divergence. Then looking at when x is equal to 6, we have the sum from n equals 0 to infinity of n cubed, and then 6 minus 5 is just going to be 1 raised to the nth power. So this is just going to be the sum from n equals 0 to infinity of n cubed. And so the limit as n approaches infinity of n cubed equals infinity, and so this also diverges by the test for divergence. And so both of these endpoints both diverge, which means we cannot include either one of these. And so our interval for convergence is going to go from 4 to 6, and then the radius of convergence, r, is going to be equal to 1, which again you can find either by looking at that absolute value of x minus 5 once it's isolated is less than 1, or you again could look at 4 to 6 and figuring out that that distance there is 2, so half of that would be a distance of 1, so r is equal to 1. So we have 2 more on the next page, and I'm going to go ahead and circle both of these examples, and we are going to try these together in class.